Hello everyone, I'm Yassine. I'm a PhD student in Polytechnic in France. Currently, I'm doing. Currently, yeah. Can you hear me? No. Can you hear me? No. Yeah. So I'm doing research visit currently at the University of Oxford. This ICML paper was done during a research visit at New York University last summer. It's about generalization of graph neural networks. So it's a new topic, different from the previous talk. So I'll try to give a slight introduction about it. So we talk about graph structured data when we have a combination of a structure, which is represented by a set of edges, a set of node. Like here, 8 gray nodes that represent the nodes, and this pairwise relation between them is the edges. And in addition to that, we assume that we have some data on the nodes. So when we combine all these features on each node, we have the node feature matrix X. And in this area, we usually say that graphs are ubiquitous because they arise in many contexts. For example, we can have a graph of political web blocks if they have a hyperlink between them. In biology, molecules are graphs where atoms are linked by chemical bonds. And what can we learn from graphs? So among these are the tasks of node and graph classification. For example, in the first example, we can classify nodes which are political web blocks if they are republic or democratic. The second example, we can classify the whole graph, like the whole molecule, and predicts one of its properties. So GNNs are just neural networks that perform on graph structured data. And the most known scheme in GNNs is message passing neural networks. So it's as any neural network, it's just we stack many layers, and each layer we use 2 steps. The first one is the aggregate. So we take the information from all the neighbors, like in this diagram, the number 2 take information from node number 1, 4, and 7, and it aggregates. So you can use any aggregation you want. The most used one is graph convolution network, which just multiply the normalized adjacency matrix by the feature matrix. And the second step is the update step. So we just take the information from the neighbors and the previous information of that node, and we just combine them. So here we do that, but by multiplying by a linear layer and the activation function. So yeah, to build a deep GNN, we just iteratively do these 2 operations. We aggregate to update, aggregate to update until we have a final representation of the node and of each node. And then if we want a representation of the whole graph, we just do some aggregation like the sum, the max, or the mean pooling. Yeah. Yeah, I'm gonna go pretty fast on that slide. So GNN have been used a lot in both research to study expressivity, over smoothing, over squashing, or robustness to adversarial attack, and also in industry. Google Maps used GNNs to predict the time arrival. It's been used in recommendation systems and in social networks, and also in biology, where it's helped to the discovery of 2 new antibiotics the last few years. So today I'm gonna tackle another problem which has been a lot of people have been discussing the last few years, which is the generalization of graph neural networks. So we train a GNN on a distribution, and we want to see if it's generalized well on other type of graphs. So why it is complex on graphs? Because the shift can be in different manners. So there is first the structure. So we can have some patterns or topology in the training set, and in test set we have different patterns. It could be, for example, in the size, and it could also be at the level of features. Or like there is some case where we have both, a combination of both shifts. So this is why it's complex on GNS to study generalization for GNS. Yeah, so yeah, forget. Like to tackle this problem, there have been different research directions. There have been some PAC bias bounds, or some Rademacher complexity bounds, some architecture refinements. And one of the methods is data augmentation, which we'll be tackling today. So I'm gonna give a general framework about what is graph data augmentation. So we have a training graph, GNYN, with the labels, and we use a sampling strategy or an augmentation strategy that I'm denoting by A lambda. Lambda is a parameters. And so I'm generating M new samples, GNM and YNM. To give you an example, it could be drop node. For example, I'm taking randomly an edge, and then with the lambda is a Bernoulli parameters. So I'm just flipping it into a non-edge or a non-edge to an edge using these lambda parameters. So the classical training assumes that we have data sets and we optimize the empirical risk, and we have an optimal parameters. And the augmentation settings, we just include those augmented into the training data sets, and then we optimize the new loss function. So, and we obtain a new optimal parameters. What we want to study is just, we have two type of parameters, which one is in the different setting, and we want to see which one gives the best generalization. So for that, we are going to study two terms. The first one is generalization gap, which measures the expected value of the loss function under the two optimal parameters, and the Rademacher gap, which measures how much GNN can fit to random noise. Yeah, this is the first theorem, which is the main theorem of our work, which says that if we want to minimize the generalization gap is upper bound by Rademacher complexity of the augmentation settings, which is also upper bound by these terms in blue that we want to control. So let me give you a few insights about this theorem. It's actually a trade-off. So to have the generalization gap here different from zero, we need some diversity in the training set that we are adding. But at the same time, if the upper bound as equal to zero is like if you are not doing augmentation at all. So what this theorem tells us that if we have some kind of diversity, so we are ensuring that eta is different to zero, this generalization gap is different from zero, and at the same time we are controlling those bounds in blue, then we are sure with a high probability that we are making the generalization better. So those terms in blue just tell us that the augmentation that we are adding to the training set should not deviate too much from the training distribution. So here's GRATIN, which is our pipeline. We call it GRATIN because it's a French dish and we are in French school. So the first approach, first step in our approach is just to train a GNN without any augmentation. So we have the message passing layer that represents in the previous of this talk. Then we have this readout function that combines the node prediction, node representation into one representation. So for each graph, we have a representation. And then the post readout function, which is just an MLP. So the second step, just we are embedding those graphs, so we are taking those representation here. So for each graph, we have a representation. And then we are splitting the graphs. So we are taking the training data set and we are splitting it by class. So because we know the label, so we can do that. And for each class, we fit and sample a GMM. And then we sample new representation that we're going to use in the training set. And the last step, we're gonna fine tune only this part here on the whole the training representation and the augmented representation. So this is different from what have been done in practice, because usually they do data augmentation at the level of input space. So I'm gonna explain why. But one thing we need to keep in mind is just also all the architecture, also for the baseline, we are keeping the same model. So we have a message passing layer, a readout function, and a post readout function. Yeah, so the first reason why we use header representation instead of the input manifold is just because it encodes both structure and features. So mainly, most of the baselines, they either do augmentation at the level of features or the level of structure. The second thing is that we want to control this distance here, but we need to do some graph alignment. So we need, if you have two graphs, you need to find what is the best permutation that allows us to compare the two graphs, because we don't know the ordering of nodes, which is difficult. So baselines do only some heuristics. For example, they can order node by degrees. So we avoid this because we are working on the header representation of those graphs. And the third one, which is most important, so we have this theorem that tells us that when we do data augmentation, it should depend on the GNN architecture we are using. Usually, they do the same data augmentation for all the GNN architecture, which is not true. This equation is based from the influence function theory, and it gives us a closed formula that if you add an augmented graph here, GNM, to the training set without training on that augmented set, we can know in advance if it's gonna help or not to improve the prediction on the test set. So we can see clearly that it depends on the gradient and the Hessian. So what does this mean? That the data augmentation should depend on the message passing scheme that we are using, which we are doing here, because it does in our case because we are doing it at this level, and it depends on those message passing architecture that we have chosen. Yeah, this is an interesting slide. So those scores there, they told us if the augmented sample that we add, if they're gonna impact positively or negatively on the test set. And we can see that most of the case, the influence score are positive. And we found some behavior that's in for GIN. So we use two models, GCN and GIN. We have a case where the influence score is almost 0. So what does it mean? That we don't have any impact on the augmentation, have no impact on the test set. So it's like if you're not using augmentation. Just to give you an insight why it does happen, because here GIN is an expressive graph neural networks, and it have no normalization here. And DD is known to have that node have a large number of neighbors. So when you sum these, they have an exploding values, and it causes softmax saturation. We have checked that like in the experiment. Like here is the part of the results where we compare, where we see the advantage of our method for both in distribution and out of distribution generalization. So we compared with the non-augmentation settings with some simple method like drop node, drop edge, and some mix-up based technique. So mix-up is just a method where you interpolate two inputs and also the labels. We can see that we have clear advantages in many of the case. And for the second table, what we did is just we take 10% or 20% of pair of nodes, and then we flip randomly edge into non-edge or non-edge into edge to create this out of distribution shift. We do that only for the test set. Yeah, another advantage is the complexity of our method. In graph data augmentation, usually either you choose a simple method, but it does not perform well. To make it perform well, what they do is just you add several iterations, several augmentations. So for example, for each training graph, use 20 augmentation. So does it mean that we're increasing the training size by 20 times? So the training time become very large, but the augmentation time is small, but the training time is very large. At the other side, there is some method like submix, where it's very powerful, like it's only one augmentation per training graph, but like to generate those, sorry, it was GeoMix, to generate those augmentation, it takes a lot of time. For our case, it's pretty, like it have the best trade-off because we only refine tuning this post-reduce function, and the GMM we can use scikit-learn, which generates in maybe 2 seconds. Yeah, I have 2 more slides. The first one is just why we use GMM. We could have used any other generative models that fits those data. So the first one is for computational reason. It was pretty fast to fit those hidden representation and sample from them. So then we have this Gaussian mixture model are a universal approximator of densities. And the third one is just we want to control this term, and you can see that we can have an upper bound that about the Kyle divergence and the supermom distance between those two. Maybe for time I will not discuss too much about this. But maybe later if you have a question about it. Yeah, and the last important part, last contribution of our paper. If you remember this influence score that I gave the formula about it before, we can use it to filter those augmentations that we are generating. So for each training graph GNM lambda, we can see what is the average influence on the test set. And because those influence score, we use the gradient and of the loss function, so we need to have the label. So instead of using the test set, we use the validation sets. And so we can rank them from the best augmentation to the harmful one. To give you an interpretation, what we want to do is just all the augmentation which have a negative influence, we want to remove them from the augmentation set. And we do that, so once we rank them, so we keep only the percentage 1 minus p, and we can see that when we are removing the most harmful augmentation, so the accuracy increase, and then it decreases at the end, because here is like if you are not using augmentation at all. Yeah, that was all. I hope you enjoyed the talk. Okay.